All right, today we're going to look at a couple special functions. The first one is called your greatest integer function. Don't hate it. So notice these weird little bracket things you have around there. That says that your equation is going to remain at an integer until it gets to the next integer. So first off, you have to remember what is an integer. An integer, remember, is like a whole number. It can be positive or negative. Okay, but you have like no decimals, no fractions, nothing in between. So looking at the parent function, these are your parent functions of this graph. When I plug a 0 into the greatest integer function, I get a 0, right? That's pretty obvious. If I plug a 1/2 in, since 1/2 is not an integer, it's going to round it down to a 0 until you plug in a 1. When you plug in a 1, the greatest integer, the integer of 1, is 1, so your graph jumps up here. So it's continuous until you get to 2, and then it jumps to 2, and it's continuous again. So kind of sometimes these are called like step functions. It's kind of a little bit inaccurate, but this is your parent function of this graph. The domain of this graph is all real numbers. The range is kind of tricky. It's all integers. So one thing you can do for that is you can do, remember Z stands for integers. Usually like the R for real numbers, we do a little double bar on the Z. That's fun to write too. Okay. Absolute value parent function, we have already worked with that this year, so I'm not going to really do much with it. We'll just go ahead and skip down to the examples. Okay. So looking at this first greatest integer function. Okay. So think transformations. What does a 2 in front do? Usually it's a stretch. It's still going to be a stretch. If I plug a 0 into this function, I'm going to get a 0. If I plug a 1/2 into this function, it rounds down to a 0. 0 times 2 is still 0 until I get to 1. When I plug in a 1, the greatest integer of 1 is 1. 1 times 2 is 2. So here at 1, it's going to jump all the way up to 2. Again, like I said, think stretches. Again, jump up 2, jump up 2. I don't have room for that. Same thing down here. It's going to be from here to here, from here to here. Okay. Tricky here on the domain. Domain, still all real numbers. The range is only going to be even integers. And 0. Tricky. For the question number 2, technically a 2 inside is a horizontal stretch of compression, and we're not going to do those in this class. That's going to be something you're going to look at more in pre-cal. So for purposes of today, that 2 is not there. This is just the absolute value of x plus 1. You've done this before. A plus 1, if you remember, moves to the left 1. If I go left 1, put my dot. From there, it's just your traditional absolute value equation. Remember your points. They're mirrored on either side. Domain, all real numbers. Range, y is greater than or equal to 0. Here's another greatest integer function. Again, up 4. Think translations. Going to go up 4. So my first point, again, if I plug in a 0 there, the greatest integer of 0 is 0. 0 plus 4 is 4. So 1, 2, 3, 4. Put my dot. From there, it's still just your normal step equation. It's going to stay at 4 until you plug in a 1. Then it's going to jump up to 5. Going to jump up. Going to jump up. Same thing here. Notice the closed circle and your open circle. Domain, all real numbers. Range, all integers. Okay, tricky, but not too bad. The next equations we're looking at on here are more special functions. These are called piecewise functions. Piecewise functions. You have several different equations that are defined specifically on one domain. So, lots of things going on here. I think it helps to maybe use some, I'm going to use some different colors to just kind of visualize this a little bit better. So first thing I traditionally like to do is kind of mark out my domain here. I have one equation from 0, when x is 0, that's right here. Just kind of drawing a dotted line just to kind of help me out. The other one is between 0 and 2. and then from 2 and on to infinity. So I'm going to start with our first equation. I'm going to do that one in, how about blue? Just graphing the line x plus 2. Well, you know how to graph that. It starts at a positive 2, right? Notice this is not equal to 0, so at that first point, I'm going to have to put an open circle. From there, I just have a slope of 1, so traditionally I would go up 1 and over 1, but that's not in my domain for this graph. So I'm only going to have to draw the side of the graph that's less than 0, which is the side over here. When I do that, I can connect all those dots, and it's going to continue in that direction. Okay, looking at the next portion of my graph that's only between 0 and 2, notice it's equal to both 2x plus 5. Again, I start at 5, so 1, 2, 3, 4, 5. Closed circle there because I'm equal to 5. From there, I can do my slope. It's 2, so that's an up 2. This is a terrible question. And over 1, up 2 over 1. Again, closed circle there because it is equal to, and I can connect my lines. I'm sorry that we had to go off the graph. I forget to change that every year. The last equation is negative x plus 1. Negative x plus 1. It's only when x is less than, not equal to 2. So this one's a little trickier. You might have to kind of, I like to call it ghost it out. So traditionally it would start at 1. This point is not in my domain. I have to keep going until I get to the part of the graph where it actually exists. So my slope is a negative 1, down 1 over 1, down 1 over 1. Now I'm on the part of the graph that actually exists. Open circle, because it's not equal to, and then I can just continue my line from there. Down 1 over 1, down 1 over 1. The other option, if you want to find where this graph actually starts, is to plug that value in for x. If I plugged a 2 in for x, negative 2 plus 1 is a negative 1. That tells me the first point on my graph was right there. Okay, nice. Looking at this next graph, and I hate this one too because it's negative 7. Let's change this just a little bit. Let's make this like a negative 2 because I can do that. Okay, I might regret that, but that's what I'm going to do. So again, first graph, first thing I like to do is sketch out that domain from negative 2 to 0, and then 0 on. Starting with my first equation, negative x minus 4, only when x is less than negative 2. Again, I know that would start at a negative 4, and then it would go down 1 over 1. But that's not the part of my graph that exists. It's over here. So to finish out that line, negative 4, it goes this way, this way. This is the first point where my graph actually exists. Open circle because it's not actually equal to, and then I can continue my line on this side of the equation. Again, it carries on infinitely in that direction. For this next equation, 5x minus 1 between negative 2 and 0. Again, these are both equal to. So here, your y-intercept at negative 1, that's actually a point on this graph. After that, it has a slope of 5. So that means up 5 over 1. But that point is not on this graph. I would need to go the other direction, 2, 3, 4, 5 over 1. Again, if I continue down, I hate this. It would actually be a closed circle here on the bottom. Actually, let's just change that for good measure too. Let's make that a 2. I just change everything to 2's. So if that was my slope, I would have to go down 2 over 1. That's a point on my graph, down 2 over 1. Closed circle there, both equal to, and I can connect those points. The last portion of my graph is a 2x plus 1 when x is greater than 0. Notice it's only greater than, not equal to. So at a positive 1, I'm going to have an open circle, and then I can just graph my line normally from there. Up 2 over 1, up 2 over 1, and it will continue on infinitely in that direction. A last example. Again, check out that domain, 0 and 2. Starting with my first line, just x over 3 when x is less than or equal to 0. So what is the y-intercept of that graph? It is 0. My first point is right here. X over 3 means up 1 over 3. Again, I only have the negative side of this graph, so I'm going to have to go down 1 over 1, 2, 3, down 1 over 1, 2, 3. Again, it would continue on infinitely that direction. The next portion of this equation, 2x minus 6, only between 0 and 2. Notice it's not equal to. So my y-intercept negative 6, 1, 2, 3, 4, 5, 6, open circle, because it's not equal to. My slope is 2, up 2 over 1, up 2 over 1, another open circle, also not equal to, connecting those 2 points. That is the only portion of this graph that actually exists. For the last part, y just equals 1 when x is greater than or equal to 2. So here at 2, or in general, that means that I just have a horizontal line at 1. So it's not going to start until I get to 2, closed circle, because it is equal to, and I just have a straight line going in that direction.